Afternoon, everybody. I realise that I'm the only person that's standing between you and beer, so I apologise for that. So I'd like to talk today about the rationale for continuous delivery. I'd like to talk a little bit about why I think continuous delivery works. I've been working in software development in various capacities for a very long time, as you can tell by looking at me. And over that time, throughout all of my time of doing that, then we've talked about software being an industry of change. And I think there's a degree to which that's true. But quite a lot of the change is kind of froth on the top. There's quite a lot of change that goes on. If I'm honest with you, I could care less about what the latest JavaScript library is this week. It changes quickly. And yeah, it might be good, it might be interesting, but it's not fundamental. And I think there's a different kind of change. I think that there are more fundamental changes that happen periodically. And those are the big steps. Those are the big steps that make us reevaluate what software development is all about. And I believe that continuous delivery is one of those. And I'm not saying that just because I was involved in writing the book or I do consultancy on that subject now anymore. But I think that genuinely it allows us to create better software faster. And I hope over the next 40 or 50 minutes, I'm going to convince you of that and give you some insight into what's going on. I think if you look at the history of software development, it's probably wise to take these sorts of industry surveys with a deep pinch of salt. They're not scientifically rigorous. They tend to be self-selecting groups of people reporting on the projects in which they work. And yet they do tend to tell a fairly consistent story, and that story on the whole is fairly depressing. This last one is kind of funny in a macabre sort of way. 17% of large projects go so badly that they threaten the existence of the company that began them. That's not a history of success. I think that if software projects were normal things, we ought to see a normal distribution. As many software projects should finish ahead of schedule, under budget, delighting their users, as finish over budget, behind schedule, and pissing off their users. But I don't think that's the picture that we think of as normal in our industry. I think this is the picture that we think of as normal in our industry. And that's a problem, because it colours the way in which we think about software development. It colours the way in which we provision projects. It colours the things that we do, the way in which we organise ourselves, the way in which we invest in software. And all of that sort of stuff has an effect of what's going on. Here's an animation that I've found that delighted me. This is showing two different views of the solar system. The first on the left is the heliocentric view of the solar system, where the sun's at the center of the solar system. And the one on the right shows the geocentric view of the solar system, where the Earth is at the center of the solar system. This was the model that humanity held of the orbits of the planets for millennia. And it's horrible. It's complicated. You end up trying to do all of these weird things which are called epicycles, and people build complex clockwork machines to try and trace the orbits of the planets to figure out what's going on. They tried to come up with the maths to be able to predict where the planets were moving, and still it wasn't. All right, if this is the view of the solar system that you hold, Newton can't come along and come up with inverse square law. This is not an inverse square relationship. A couple of centuries later, Einstein can't come along and come up with ideas of general relativity with bendy sheets of space-time. Those are not conclusions that you can reach from this model. I believe that this is a great analogy for where we are in the software industry. I believe that a large proportion of software development is based on this kind of model. And we can't extrapolate. If we get the right model, things become simpler and more straightforward. So I think that we ought to be looking for the right kind, a better kind of model. So I would argue that the state of software development has been kind of suboptimal. It's not really ideal. But I would also argue that in just the last few years, there have been signs of change. I think we've been learning. I think we've genuinely been starting to understand what it takes to build high-quality software effectively. And I chose this picture kind of carefully because it's not polished. It's not cookie cutter. I can't just kind of stamp out a process for you that's going to be perfect. Each one's going to be handcrafted and tailored to meet your needs. But nevertheless, I believe that there are some foundational characteristics of good software development that are common for all software. So what have we tried? We've looked at other industries over the years, and we've come up with waterfall models and V models, if anybody except me is old enough to remember those. We've tried to subdivide the problem into small chunks, and we've ended up building silos where we've handed the silos between the different parts of the organization. We've tried adopting more iterative approaches, and we ended up drowning into bureaucracy with that particular one. We've tried adopting project management approaches like Scrum that allow us to move forward. Anybody, any idea how often the documentation for the Scrum process mentions the words software or code? None. Scrum's a really nice project management process. It's as good for plumbing as it is for software, but it says nothing about software. So we've tried things like adding some more engineering practices like extreme programming. We've tried hiring really smart people and putting them in the corner somewhere. We've tried hiring young smart people because they're cheaper. And we've tried hiring young smart people in foreign countries because they're even cheaper. And all of these have some role to play, but these are not the answer. Here's part of the problem. This is a document that was published in 1970. It was written by Dr. Winston Royce. And this was published for an IEEE conference. And this is the document that for the first time introduced the concept of a waterfall process associated with software development. This is the first time that waterfall process was used in the context of software development. So in one way, the IEEE has a lot to answer for. Here's the famous picture. Everybody's seen this picture, right? Everybody has seen this picture at some point in your career, yes? This is on the second page of the document. This is the next paragraph, and I've expanded it so you can read it. It says, the implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development phase, is the first event for which timing, storage, input, output, transfers, etc. are experienced as distinguished from analysed, and these phenomena are not precisely analysable. So the document that introduced the idea of waterfall development into software was saying, don't do waterfall development. Unfortunately, the picture is really compelling. You can imagine reading the documents and going back to your team, reading the document, getting to the second page, says, oh, I understand what the document's about now, not reading the rest, of course. Going back to your team and drawing that on whatever the 1970s version of a whiteboard was, and the last 40 years of software development is the consequence. This is the document, this is the diagram that he was actually recommending. This is on page 7 or 8 or something like that of the document. It's not quite so easy to get into. However, with the benefit of 21st century hindsight, there's some really interesting bits in here. It talks about testing must be planned as a vital part of the development exercise. It talks about concretely establishing feedback loops from testing into program design and from program design into software requirements. With the benefit of 21st century hindsight, we can look at this as maybe being a form of agile development. Maybe. So, here's a picture that kind of characterises what we're talking about. This is a quayside in the west of Ireland, in the northern hemisphere where I'm from. And you can see that there's a car that's fallen into the water. So what do you do when something like that's happened? You get a crane. Right? Oops. What do you do now? Any ideas? Can you see where this is going? Einstein said, that the definition of insanity was doing the same thing over and over again and expecting different results. So if our software development processes are not fulfilling our needs, if they're not delivering the quality of software that we want, if they're not delighting our users, if they're not getting it in on time, if they're not being able to come sometimes at least under budget, maybe we should consider trying something else. Maybe we should consider trying anything else than what we've been doing. So let's go back to first principles. I would argue that any organization that practices software development wants this. I think that every organization, whatever its nature, wants to be able to have an idea, get that idea into the hands of their users, and figure out what their users make of the idea. That's pretty much what we are all paid to do. Whatever our capacity in software development, that's our job. So I think that's a good starting point. I think we should be optimizing to do that. Have ideas, get them into the hands of users, and figure out what our users make of those ideas. I want to pose a question. What's the most successful invention in human history? And here are some pictures that are meant to intentionally mislead you. Any thoughts? Wheels? Language, wheels? Beer. I've got beer. I like beer. I would argue, I think somebody said it over there. I would argue without much fear of contradiction that it's this, science. And I don't mean space shuttles and gravitational wave detectors and quantum physics. I mean the simple four-stage process of looking at something, figuring out an experiment that could forming a hypothesis, figuring out an experiment to test the hypothesis, running the experiment and reflecting on the results. Pretty much that's it. If you look at the whole of human history, we've been around on this planet for something in the order of about 200,000 years. And if you graph the effectiveness, the capability of humankind, by almost any measure, the distances that we travel, the amount of information that we process, the number of connections that we have with other people, the energy that we have, that we wield, the resources that we consume, all of those things, it's pretty much a flat line through the entirety of human history. And about 200 or 300 years ago, starts to tick up very gently. Through the 20th century and the 21st century, it just goes vertical. On any graph where you can get all of that in, it's basically a straight line and a straight line. That's the graph of human progress. There's data that suggests that the whole of human knowledge doubles once every 14 months. That's staggering. What happened 200 or 300 years ago? Well, it was the age of the Enlightenment. It was the introduction of and the application of science and engineering for us to solve complex problems. That's the roots of our modern technological society. I would argue that software development is one of the more complex, difficult things that human beings undertake. I would argue that we build this weird, intangible, ephemeral, abstract stuff in teams trying to solve problems that we don't yet quite grasp and can't quite tackle with. I suggest that we should be applying our strongest problem-solving technique to those problems. And yet, I don't think that's how mostly we work. I think if you're honest and you think about most of how you work, a lot of it's based on guesswork. It's certainly in my career that's been the case. If I look back on my career, I've spent a lot of time guessing what my users might like. I've spent a lot of time guessing whether my solution is going to fulfill those needs and whether it's going to scale and whether the architecture is going to grow over time and whether they're going to like the color of this button or whatever it is, making guesses. And that's not good enough. I'd like to be able to carry out experiments. I'd like to be able to learn, adapt, evolve. So what am I talking about? This is what Wikipedia says the scientific method is. We want to make a guess based on experience and observation. We want to propose an explanation. We want to make a prediction from the hypothesis, and we want to test the prediction. That's it. I think that if that was all I had to tell you, I think that's pretty good stuff. I think that what we're talking about here is starting to apply some real engineering discipline to the things that we do. Engineering discipline in the sense of applying science to practical problems, which is certainly one definition of engineering. Again, I think on the whole, it's not how we tend to approach things. But that's not all I've got to say. There's more to say. Let's go on a bit further. Let's look at some more data on projects, and on the whole, it is a picture that says waterfall's bad and agile's good, and here's some more pictures that says waterfall's bad and agile's good. This one's particularly amusing in that if you invent your software development process from scratch, slightly better than waterfall. The top line, though, is the interesting stuff. That's more iterative stuff. And the reason that that's important is because it gives us opportunities to learn. It gives us opportunities to carry out, even if we're not thinking about these formally as experiments, it gives us opportunities to carry out experiments, learn, adapt, and refine our understanding of things. Lean stands out as particularly strong from there. So what's that about? Lean is really focused on maximizing our ability to learn. And part of that is we want to deliver changes very quickly in small pieces. We want to do that to maximize our opportunities to learn and adapt and to refine our understanding. If we want to do that, we need the change to be durable. We can't afford to make the change and then have to go back and keep patching it and fixing it and addressing the poor quality in it. So we need to think about quality from the outset. We need to build quality into the system so that we can carry out our experiment, understand the results, learn from them, and move on. We want to be able to optimize the whole process. If your software development process, you spend weeks and weeks optimizing your deployment into production, but the problem is in your requirements capture, or you've got a 5-year backlog of requirements, you're not looking at the whole picture. You need to think about the whole picture and figure out how to make all of it work efficiently and effectively. It's about eliminating waste, and I've just pulled out 3 different kinds of waste. Unnecessary variations. A few years ago, I worked on a project where we had 7 different mechanisms for persisting our object model into a relational database. That's not efficient. That's not a good design choice. Every single time you needed to persist something into a relational data. Oh, sorry. Sorry about that. I don't even know what that is. Okay. So every single time that you wanted to persist something into a relational database, you had to, I haven't used this one for ages. How does this one work again? This has that unfortunate bug. I'm just going to run into that with this change right now. It's just a waste. The other one that's kind of absolutely endemic in our industry, I'm a consultant. I go into other people's organizations, and so I have that privilege of just standing slightly aside and watching other people and kind of laughing behind my hand sometimes. And one of the things that they all say, oh yeah, what you're talking about, Dave, is really good. We would really like to do that, but we haven't got time. We've got all these features to deliver. Overburden is one of the most effective ways of slowing a team down. Part of my background, working with Martin over there a few years ago, is in high-performance systems. And one of the things that you think about a lot when you talk about high-performance systems is the efficiency of queues. And if you start to think about the load of queues, what's the way of maximizing the throughput of a queue? Well, you could think of not putting anything into it at all. That's at one extreme, and clearly that's not going to maximize the throughput of the queue because nothing's going to go through the queue. The other end of the spectrum is that you could fully load the queue. You could have the queue completely full, and that's not going to be the most efficient either, because every time you come to put something into the queue, you've now got to wait for something to go out of the queue. And so you're going to be working very slowly. You're going to be working at the rate of the consumption plus a bit. It's going to get worse and worse over time. So what's Little's law? It kind of will tell you sort of throughput, and it's more complicated than I am making it sound. But roughly, it often comes out that if you look at about 70% load, is going to be the maximum throughput of the queue. Information is information. Information flowing through a team is flowing through a queue. There's no real difference there. Just because we're clever and we're in the middle of the queue doesn't make a difference. If you maximize the load on a team, if you make sure that they're always fully loaded at their maximum capacity, they will go slower and slower and slower over time. If you want to maximize the efficiency of a team, you've got to back off, you've got to slow down, you've got to put less load on, you've got to give the team time to understand the implications of their work, do high quality changes, find ways of improving themselves, and have the time to undertake those changes. And the last one is the last form of waste that I've pulled out here. There are others, but wasteful activities, doing things that are useless. So doing bureaucracy that doesn't add any times, building again if over and over again to deploy to different targets. All of those things are costs that you don't need to incur. So we want to work efficiently. Lean is about being very efficient and effective in our approach to process. Modern lean practitioners talk about you optimize for learning above all else. If you optimize for the learning of the team, you will maximize the throughput of the team. If you optimize for the throughput of the team, you'll make the throughput worse. It's counterintuitive, but that's the way that it plays out, and there's lots and lots of example and data to show that that's true. We'd also like to make decisions late. We'd like to make decisions late so that we've got the best possible information at the point at which we make the decision. That one of the things that's horrible about waterfall is the cost of change curve that it talks about, the classic kind of exponential cost of change. If that's the world that we live in, then it means that we should be making all the most important decisions on our software project at the point at which we know the least that we will ever know about the software project. That's not a recipe for successful decision making. And finally, we need to empower the team. We need the people that cause a problem to be in a position to witness the problem because they're going to be best placed to fix the problem. I've come to think of software development pretty much like this. This is a simplified view, of course. But essentially, what we're trying to establish is a series of feedback loops. And the feedback loops are crucial to being able to make this an effective process. At the outside is the feedback loop that I mentioned before, the one that employs us all. Have an idea, get the idea into the hands of our users and figure out what they make of it. At the inside is the classic TDD feedback loop. You write a test, you see it fail, you write some code to make it pass, you tidy it up, you commit, you move on. And in between, we've got executable specifications, all to give us feedback and insight into the work that we're doing constantly. You can probably tell from the nature of my talk that I'm a bit of a popular science nerd. And this is one of my heroes. This is Richard Feynman, the Nobel Prize-winning physicist. Feynman, without much fear of contradiction, Feynman's probably one of the finest minds that we've created as a species. He was a genius of the first order. He came up with a way of doing calculations in a field called quantum electrodynamics. They're 3 orders of magnitude more accurate in their predictive power than general relativity, which is no mean feat, since that's a remarkably powerful tool. This man was a proper genius. And he said, it doesn't matter how intelligent you are, if you guess and that guess can't be backed by experimental evidence, then it's still a guess. So I think we should be trying to get ourselves out of the realm of working based on guesswork. I think we should be trying to get ourselves into the realm of carrying out experiments, learning, adapting, refining. The experimental thing is kind of fundamental to my message, and I think when I've had a few beers and I'm feeling expansive, I think that maybe what we're on the bottom ladder, the bottom rung of the ladder for, is defining what software engineering really ought to be, a genuine engineering discipline for software creation. This is another part. This is another rung on that ladder. This is the idea of cycle time. I'm going to show you 2 cycle times from 2 projects that I worked on. The idea of a cycle time is imagine the smallest change to your production system and imagine that change going through all of the steps in its normal process that it ought to go through. So somebody deciding that the change should be made, somebody prioritizing it for a team, somebody putting it on the backlog for the team taking it, testing it, deploying it, all of that stuff. And I'm going to show you these 2 feedback loops. The first one was from a project, it was an order management system for one of the UK's big banks. And they had a cycle time of 103 days. If you've got a cycle time of 103 days, you don't have a feedback loop. If somebody comes to me after 103 days and says, Dave, you just broke in production, I'm going to say, what? I was on holiday then, surely. I'm going to say, couldn't have possibly have been me. Maybe it wasn't my code. Maybe it was my code and Martin's code that bumped into one another. And I might be right. If I've got a cycle time of 103 days, then what's going to happen is every 103 days there's going to be a huge mountain of changes that are going into production. And those changes in themselves constitute a huge bundle of risk and a huge level of complexity that's going to be hard to understand the impact of if something goes wrong in production. The next project was a project that a few of us here at this conference worked on. We were building one of the highest performance exchanges in the world for financial trading. And this project, in terms of scale, was roughly something like 15 to 20 times more complex than the project on the top. The project on the top would have been one component in this system. We had a cycle time on this project of 57 minutes. We could evaluate any change destined for production and get feedback in 57 minutes, after which there was nothing more to do before we were happy to release it into production. There was no more testing, no more validation, no more sign-off. We were ready to go after 57 minutes. If you've got a cycle time of 57 minutes, the game's changed. If somebody comes back to me after 57 minutes and says, Dave, you just broke in production, I'm going to remember what I was doing. And better than that, the number of changes that are going in every 57 minutes are going to be small. It's going to be simple to understand what's going wrong. It's going to be easy to figure out how I screwed up and how I caused the problem. Worst case, I can probably just back out the change, figure out what was going offline, and then resubmit it. At one point, we decided we didn't like the commercial terms that we had with our relational database vendor for our data warehouse. And so we changed to another one. We made the changes necessary to deploy the new relational database system, automated, of course. We ran them through the pipeline, and a few tests failed. We fixed the tests, we ran it through the pipeline again, all the tests passed. The next time the system went into production, it went with a new version of the database. I've worked in organizations where just that would have been a 6-month project. This changes the game. The idea of this short cycle time drives good behaviors across the board. As far as I've been able to tell so far, this is an ungameable metric. I don't know how you can achieve a cycle time in the order of minutes or hours and not be good at all of the things that you need to be good at. It's not a silver bullet. It takes an awful lot of work to get this good. You've got to have a great story on team organization. You can't afford siloed teams because the handovers will kill you. You can't afford large teams because the communication overhead will kill you. You can't afford anything but a great story on test automation, deployment automation, configuration management. All of those things have to be in great shape to have this kind of cycle time. But if you can do that, it pushes you in the direction of a really healthy development process. I would argue that if you left this room now and you did nothing else except use an iterative, experimental approach to driving down your cycle time to this kind of order, you will improve your software development process. More than that, I would argue that if you did that, you will push out all of lean theory, all of DevOps, ideas, all of continuous delivery, all of agile as a natural consequence. This is a great tool. Just driving to reduce cycle time will force you to get good at the things that you need to be good at. Oops, sorry. So let's start getting into a bit more detail. So what's continuous delivery? So first of all, it's the first principle of the Agile Manifesto. Our highest priority is to satisfy the customer through early and continuous delivery of valuable software. Have an idea, get it into the hands of our users, and figure out what they make of it. It's kind of the logical extension of continuous integration. Continuous integration is the process that it was practiced widely before this, but it became popularized and applied that name kind of roughly the beginning of this century, And it's about developers evaluating their changes quickly and efficiently so they can understand the impact of their changes. And that's good, but if you can kind of stretch it out just a bit further, it's even better. And continuous delivery is about that. It's just extending the range of continuous delivery a little bit further. I like to think of it as a holistic approach to software development. I'm talking to you on a DevOps track. I'm a big fan of the ideas of DevOps and the principles. If I'm honest, I hate the name. I think continuous delivery is a much better name. But we're talking about the same stuff. This is a holistic approach to software development. It's about all of it. It's about optimizing from having ideas to getting valuable software into the hands of users. That's everything. That's all of our jobs. That's all of operations, all of development, all of testing, all of product ownership, all of it. A good mental model for this is to imagine that every time that we commit a change, we're giving birth to a release candidate. And then the job of our automated system is to prove that that release candidate is not fit to make it into production. That sounds backwards at first, but this is another one of those lessons that we learn from science. In 1934, Karl Popper came up with the idea of falsifiability. I can assert that all swans are white. I can never prove that all swans are white, but I only have to see one black swan to know that not all swans are not white. Similarly, I can assert that I have enough tests to say that my code is good. I can never prove that my code is good, but as soon as I see one failing test, I know that my code is not good enough. Therefore, I'm going to work in a way so if I have one failing test, I'm going to reject the release candidate. Sometimes people ask me, what percentage of tests is it acceptable to release with what percentage of test failures is it acceptable to release into production? I would say none. If you've got one test failure, you shouldn't release into production. Actually, that's the only time that a test's doing anything useful. If it's running and passing, you don't know what state you're in really. You hope that you've got some probability that it's okay, but you don't really know. As soon as it's failing, it's telling you something real. Every commit creates this release candidate. Finished means releasing into the hands into production. Actually, this list was taken from the continuous delivery book, and this is one of the things that I would change if I was rewriting the book today. Finished means in the hands of users delivering value. Released into production is a little bit too early. So what are we trying to achieve? We're trying to create a repeatable, reliable process for software delivery. If we're trying to do that, kind of rules us out. We, as a species, are not repeatable and reliable. As one of my friends said a few months ago, we're no good at for loops. Humanity, we're just no good at that repeatable and reliable. We'll go for a cup of coffee. We'll forget what we were in the middle of. We'll lose track. We'll see an attractive member of the opposite sex or the same sex walking past or something like that will distract us. And we're just not going to be in the zone all of the time perfectly. We're just not that kind of thing. Computers, on the other hand, are wonderful at repeatability and reliability. So let's use them for that part of the problem. Let's use them for the repeatable, reliable part. We want to automate pretty much everything. If we want to automate pretty much everything, we need to keep pretty much everything under version control. A good mental model I would challenge you with is imagine releasing a version of your system that was in production 6 months ago into a test environment. Just think about that for a moment, what that takes. You've got to know which version of the operating system you were running, which configuration, which hardware you were running, how the network was configured, which version of your deployment pipeline you were running, the version of the code, the version of the database, all of that stuff, everything. Software's weird. Software's unusual stuff. Most of human experience, if something's difficult and painful, it's probably wise to avoid it. Software, not so much. If we avoid it, it's going to get worse. If your release process is unpleasant and you're releasing once every 6 months, the worst thing that you can do is start releasing once every 12 months. I guarantee you it'll be more than twice as bad. If you're releasing once every 6 months, start releasing every 3 months. Start releasing every month. Start releasing every week, every day, every 57 minutes. Push it down. It will force you to address the problems in your process and your technology. Software is the stuff that's changing the world. We are the source of the revolution that's driving change in our world these days. And so everybody has a stake in the stuff that we create. So we want to be able to work our processes to be transparent. We want them to be able to be easy to understand where change is in the process for everybody, not just us techies, but everybody. We want the CEO to be able to walk past and say, okay, well, there's a bunch of tests failing, so I'm not going to get that change that we were talking about yesterday's not going to go through. We want it to be that transparent. So that we want the processes and the technology to be clear about where ideas are in flowing through into the hands of users. And you're not going to get this by buying my book or hiring a consultant or going on a training course and you know, a 6-month project. It's not going to work like that. This is a changing culture. This is genuinely, I don't like using this word because it's the sort of word that marketing people use all of the time, but this is a paradigm shift. This is a change in perspective. This is a completely different way of thinking about software development. This is as different from what most organizations practice in software development as the heliocentric view of the solar system was to geocentricists. It's challenging, it's difficult, it's going to make you think again about lots of things that you learned and lots of things that are daily common parts of your practices if you're not already doing this kind of thing. This is just me showing off. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I think that we're onto something. I think that we might be genuinely on the verge of being able to define some real proper engineering practices that allow us to build stronger software more effectively. We're not talking about small gains here. We're not talking about 5 or 10% improvements in performance for teams that practice this kind of thing. We're talking about orders of magnitude changes very often. It's common for organizations that practice the sort of things that I'm talking about to report, for example, much more than 90% drop in bug rates. It's normal, in fact, for people to talk about that kind of thing. So what am I talking about? So here's one of the ideas that's kind of central to continuous delivery, the idea of the deployment pipeline. We have some developers working, they're going to commit a change to a version control system of some kind, and there's a process that's monitoring that, and it's going to pick up that change, it's going to evaluate that change, and it's going to give fast feedback to those developers. Ideally, we're looking for feedback in the order of about 5 minutes to the developers. That's quite challenging. There are a number of different things, there are a lot of things that go into trying to achieve that. One of the key objectives here is you have to be very careful about the nature of the tests that you pick, that you can run lots of tests that are going to give you a high level of confidence in your change and get a result back in 5 minutes for a system of any size. For the LMAX system, that was the exchange that I was talking about, when I left, we were running around about 35,000 tests, doing the build, and building the deployable artifacts in about 4 minutes. They changed their build system. They got that down to 90 seconds, I believe, now. You can run a lot of tests if they're the right kind of tests, but those tests can't afford to be starting another process, talking to a disk system, talking across the network, talking to the files, talking to a database, any of those things. These are going to be in-memory, in-process tests, very close to the software under test. Guess what? The sorts of tests that you create with TDD are ideal for this. What I've described so far is just continuous integration. This is another one of those step changes in practice. The continuous integration is a wonderful practice. It's a much more effective practice, and still not enough organizations practice it. But we can go further. Where we start to diverge now is we've just built the software and we've just tested it. What we'd like is we'd like the software that we tested to be the software that is released into production if this release candidate makes it that far. We don't want to have to recompile it because maybe we'll introduce a bug because we had a different compiler. Maybe we'll link to some different libraries and introduce a bug that these tests might have found. So we'd like to be able to deploy the stuff that we've tested. So the output of a successful build in continuous delivery are the deployable artifacts. They are the binaries, the jar files, the .NET assemblies, the tar files, the zip files, the Docker images. Whatever is your deployable unit, that's what we create at the end of the commit stage. I'm a huge fan of test-driven development, that for many reasons. If you want to stop me outside sometime, I will bend your ear about test-driven development and tell you why I think it's a really important design technique, not just a testing technique. But it only goes so far. What test-driven development does is it asserts that the code does what the developer thinks the code should do. That's really, really important stuff, but it's not the same stuff as asserting that the code does what the users need it to do. For that, we need a test from a different perspective. In continuous delivery terms, we call those acceptance tests. Acceptance tests are whole system black box tests from the perspective of an external user of the system. We want to be able to run these in production-like environments. We'd like to be able to deploy the release candidate using the same techniques that we will ultimately use in production if the release candidate gets that far, so that we can rehearse the deployment and the configuration of the software along with everything else. And then we want to interact with it in lifelike user-driven scenarios. We're going to collect the results from these and store them in our artifact repository where we're storing our deployable units. I would argue that any form of regression testing done by human beings is too slow, too expensive, too low quality, and an abuse of human beings. It's a lousy job. I don't know if you've ever done it, but it's a rotten job, just being a script monkey, following a script. And certainly when I do it, I'll lose my attention. I'll go off for a cup of coffee and come back halfway through, and I'm not very good at it. But as a species, we're not very good at that kind of thing. So we use that for the automation. We never do human beings for regression testing. That doesn't mean there isn't a place for human beings, though. Human beings can bring a different sort of insight. So we are interested, particularly if there's a user interface at play in our system, we want to understand the sorts of pictures that the system paints inside people's heads when they use it. You know, does it allow them to navigate and move around to the next place in intuitive ways? Is it usable? Is it pleasant to use? Is it sensible? Have I done something stupid like code a blue button with blue text on it that nobody can read? All of those things, automation are never going to look at. They're never going to find those sorts of errors. But a human being will spot those sorts of problems very quickly. The system that this example is based on is the LMAX system, which was performance was a key criteria. As a result, I tend to use performance as a bit of a proxy for all kind of non-functional requirements. And I probably don't talk enough about the other sorts of non-functional requirements that we tested. We tested failure scenarios. We tested daylight savings changes. We selectively killed different bits of our system and then brought them back up and checked that we hadn't lost any data. We measured the performance of the system in these two different ways, the component level performance and then the system level performance. So the component level performance would tell us if I'd done something stupid in a performance critical part of the system, if I'd inadvertently slowed it down, and the system level performance, that tends to find the sorts of bugs that you expect to find, that you expect to create in performance. The system level performance tends to find the kinds of bugs that you don't expect to create with performance testing. So that's more lifelike interaction of scenarios. You know, imagine an order processing system where that also supports stock control at the same time, and you lock all the database tables while you're doing the stock control. Stop all the order processing. That would be interesting to learn during a testing run. So having that sort of interaction of lifelike scenarios is a useful exploration of the system. We'd like to be able to screw up and get the design of our data just as wrong as we can screw up and get the design of our systems wrong. So we'd like to be able to test the migration of our data to new versions as well as everything else. So we'd like to be able to evaluate that and understand that. What we did at LMAX was that we would record a daily snapshot of production data, and we would anonymize that. This is all automated. We would copy that anonymized set of data into a test environment, and then each release candidate that made it that far through the pipeline would be started up against that set of data, and we could evaluate whether that it was able to migrate the data and still looked sane at the end. If we've done all of these things and all of these tests have passed, we're going to have a very high confidence. There's nothing more that we can think of doing. If we could think of doing it, we would do it. We would add the test. Because we're experimenting. We're not just guessing. We're trying to, everything that we do, we're trying to build on the basis of knowledge rather than guesswork. This gives a very, very high standard of fidelity, a very high standard of understanding the quality of our system. The LMAC system was in production for 13 months and 5 days before the first bug impacted a user of the system. We found bugs. We even found bugs in production. But they didn't impact on our users because our system always worked. Our system always worked, but the sorts of bugs that when we did find a bug, actually after 13 months and 5 days, it was a pretty unpleasant one. But this gave us the ability to move very quickly, to experiment, to try out ideas, to develop things quickly and to learn and adapt. I have to get the pushback, okay, that sounds really nice, Dave, but it surely can't scale. It's not going to work for real-world systems. My example for that is Google. So Google have taken the unusual decision to have a single monolithic repository with all of their stuff in it. Every change is committed and evaluated together. This is old data now, but about 2 years ago, they were doing 60 million builds a year and growing exponentially, 100 million lines of code. All tests are run on every commit. There are more than 20 commits a minute. 100 million test cases are executed every day. So if your system's bigger than that, let me know. I'll be interested whether it scales bigger than that. The other pushback that I sometimes get is, oh, you're just crazy. You're talking about releasing how often? That can't possibly be sensible. My example for that is the Amazon build process. Who's used Amazon in the last 2 weeks? Which version did you use? That's a stupid question, which not even Amazon can answer, because Amazon deploy, on average, once every 11.6 seconds. Once every 11.6 seconds, a change in Amazon is being deployed to 10,000 servers. Since they've applied that approach, there's been a 75% reduction in outages. There's been a 90% reduction in the time taken to recover from outages, and less than 0.001% of deployments causes any problem anyway. The other pushback that I sometimes get is, okay, this is really nice for very simple problems like Google and Amazon, but my technology is complicated. My example for that is the HP LaserJet firmware team. Transformation of development approach for all of these projects was undertaken. They did a nice analysis of this. This is the firmware that operates inside of all LaserJet devices. To cut a long story short, you can see the breakdown of different things that they were doing before and after. They're spending, once they'd made the change, they're doing a lot of work on automated testing, but this pays back in itself. The summary of this is that overall development costs were reduced by 40%. At the same time, programs under development were increased. So you got an overall program down, cost per program down by 70%, and actually more than 8 times the amount of effort was going into doing new stuff at the end of the change to this process. What I am talking about is that I believe that continuous delivery changes the economics of software development. The data for this is coming in. We have peer-reviewed data that says that if your organization practices continuous delivery, you will make more money. Here's a summary of that. The slides will be available, so you can follow up you don't have to trust me, you can follow up the data. High-performing IT organizations, which includes, crucially, people practicing DevOps practices and continuous delivery, they're twice as likely to exceed profitability and market share and productivity goals, 50% higher market cap growth over 3 years. 66% of those organizations report significant improvements in quality. I can't work out what the other 34% are doing. Who practices continuous delivery? this is a tiny sample of organizations that practice it. And there's the kind of usual suspects are here that you would expect. Google, Amazon, those sorts of places. But also some places that you maybe wouldn't expect. Barclays is having a massive program of trying to migrate. They're on a journey. They're not there yet. But they are moving in the direction. They're moving 130,000 employees in the direction of working using continuous delivery. Volvo Trucks use continuous delivery to test all of the software in the trucks. Millions of lines of code inside the automation for trucks is running simulation to evaluate those things. As a science nerd, I was particularly proud of NASA. The Curiosity rover, that amazing piece of engineering where you have this rocket-powered sled aerobraking through the atmosphere of Mars and hovering above the surface, lowering the Curiosity rover down onto the surface via a crane. The software for that was written using continuous delivery approach because it had to work. They had to engineer solutions. There was no backup. They had to be sure that the software was going to work, and so they were simulating the system being operational. I am done, and I am 2 minutes over time. I'm very sorry, so I'm not going to have time for questions, I think, but I will be very happy to take any questions, any conversation outside afterwards. Thank you very much indeed for your time.